So welcome to the second lecture of our introduction to Haskell course. Yeah, and it's my pleasure to introduce again Brink van der Merwe and Yorick Hardy, who kindly agreed to share with us their Haskell knowledge. Yeah, and I know there is lots to be learned. So I don't know who of the two leads us today, but please, you're most than welcome to start. Yeah.
Okay, so I'll just go ahead and do a screen share.
Please.
Okay, there we go. And I guess everyone can see my screen.
Yes, perfect. Thank you.
So let's look at a few exercises. So these are the slides from Graham Hutton that I mentioned last time. So perhaps let's look here at his third exercise. So these are the slides from his chapter 2. And so he's asking to write a function that's similar to the function in the standard prelude last that selects the last element in a list. Okay, so let me just do that. Find my VS Code here somewhere. There we go. Okay, so the whole idea is here just if we have some lists, say 1, 2, 3, 4, then the function last that we write should simply return the element 4 and maybe more than one implementation of this, and perhaps thinking back of some of the functions from the standard prelude to standard library I mentioned last time. So seeing if we can do that. Let me just move. Okay, so what I'll do with last, I'll just call my version last prime, just to distinguish it from the one from the standard library, so that I don't have any naming conflict. So one potential implementation is, well, one thing we can do is we can do the reverse of a list. So if you have a list, you can call the reverse function on it. So for example, one thing I can do, say I do reverse of ups. So I do the reverse of the list 1 to 10. It will simply reverse this list 10, 9, 8, 7, 6. So well, one component, let's use perhaps reverse. And then we also had a head function. So head just returns the first element of a list. So if I take the list 1 through 10, it will just give me 1 back. So one idea could be just to take this composition of functions, reverse a list. So let's see if this works. So if I do last prime of the list 1 through 10, hopefully we get 10 back. So that's perhaps, yeah, one implementation. Yeah, and sort of notice here, it wasn't really even necessary. I can just say last prime is the composition of these two functions. It's not necessary to sort of specify parameter x's to say last prime of x's is head composed with reverse of x's or something like that. I can just do the function composition, and so now I have a new function last, which is just the composition of these two functions. So that's, yes.
Sorry if I jump in. I was wondering if you wanted to just say something about, in many languages you have variables and you have functions, and they don't necessarily work in the same ways. But here it looks like your function is a variable. Did you want to just say anything about that very briefly?
Yes, I will, and maybe you have some additional insight, or you might have some ideas that, or things I'm not thinking of sharing now. But so obviously, sort of the big problems. So normally in other languages, you have some variables that you simply mutate. You change the value of a variable, and as the computation goes ahead, you keep on changing this variable, and then you just return that at the end. So since that's not something we can do in Haskell, so that's why sort of this distinction between sort of variables and functions are not really there. Or Yorick, I don't know, perhaps you on the spot, I'm maybe not giving a good answer to that, so maybe you have some good insight to share.
I think that's a very good answer, but I would maybe say that whenever you name something, that is the role of what variables have in a language, which means that you give a name to some number, and then you can change what that name refers to, which is the binding. And here we don't really worry about whether it refers to some data or a function, because all of these are considered to be the same kinds of things. So we don't have a distinction between the functions and the variables. I think that's just the main point. So equals is equals in the usual sense, and functions can be treated just like numbers and words and anything else.
Yeah. So yeah, I think that's sort of a better explanation. So in functional programming, sort of a variable is just a function not taking any parameters. Right. So, but I can't, for example, say, well, my variable 5 is equal to 5, and then later I change it and say, oh no, by the way, it's actually 6. So I can't do something, since I already said my variable, which is really a function taking no parameters, is 5. I did that, so I can't sort of change my mind now as you normally do with variables.
So you say we lie when we say variables because they don't vary.
They don't vary, yeah, exactly. So let's look maybe at sort of another implementation of sort of this last function. So something I want to use is this higher order function that I didn't introduce last time, drop. So I can say I first give a integer parameter saying how many elements I want to drop of a given list. So I can, for example, say, well, drop the first 5 elements of the list 1 through 10. So another way of defining the last element, I can say, well, let's drop, and well, now how many elements should we drop? So we take the length of the list and we subtract 1. So now we have a list with just a single element in it that we're looking for. So now I can simply say, well, let's take, let's just take the head of that list. So this first part will give me the list back just with the single element, which is the last element. And then head is just going to return that element. So let's see if, before I explain it more, let's just see if that's working. So let's do, say, last prime 1 through 10. Oops. And it's giving, so something I've introduced here is this dollar notation. So in essence, what dollar is doing for me, if I'm too lazy to put parentheses, I can sort of, instead of putting opening parentheses and a closing parentheses, I can just put dollar down. And maybe it will be a little bit confusing, but what dollar is, it's in fact a function. But typically I sort of, or people use it since instead of having an opening and closing parentheses and so on to get the precedence right. So I really wanted sort of opening parentheses before the drop, and after, at the end of my X's, I want closing, but instead of doing that, it'll just looks cleaner just writing this single dollar, and that's what it's achieving. But it's in effect a function, and if you ask for more info about this function, you get this info back, and this 0 is just indicating the precedence. So it's a function with the lowest possible precedence that you could get. So I know at this stage maybe that's a little bit confusing, but if you think of it just as a way, if you think of it as a function, maybe it's still confusing. But if you think of it just as the way sort of I'm using it here, just as a way of not having to write opening and closing parentheses, and you see people often using that. Yeah, so that was sort of the first exercises I thought I'll look at. So then next, let's maybe look at the exercises at the end of chapter 3. And here's a function twice f of x equals f of x. And they ask, what's the type of this function twice? So perhaps just give it some thought, and let's just see any. So here's some more suggestions, other implementations, last prime of x's. Yeah, so one thing we can do, yeah, true, this is also a good idea. This double exclamation mark notation. That's sort of one way of saying, well, if you say double exclamation mark and some value, it's going to give you the value. So see, if I give 0, it's going to give me element 0 back in x's. If I give 1, I get element 1 back, and since it's 0 by 0 index based, length x's minus 1, that's the element I want back. So maybe a nice implementation is even this, we use the double exclamation mark to say you want the last element back. Yeah, so Zirap is saying exactly, mathematically a variable is a function whose domain is a singleton, and codomain is the type that the variable has. Yeah, so that's a much better explanation that I could come up with. So let's look again this function twice. So I'm interested in twice of f so yeah, I'm just giving twice these two parameters, and it's just f apply to, let me just make sure that's exactly what they ask for. Yeah, twice of f of x is f of x. So this is what we're interested in. And we want to know what is the type of twice. Okay, yeah, it's sort of indicated here. So what it's doing is you have to give it a function that takes any type any polymorphic type t to t, and then it will return another function that also goes from t to t. So the type inference of the compiler is clever enough to figure out, since I'm composing these functions, the original function can only go from t to t. It can't go from a to b. Yeah, so if I do, say, let's use it. So if I do, say, twice of, say, something like +5, and I apply that to 10, so it seems it's not happy with me here. Let me see if I do this. Let me just maybe also sorry, let's just reload, and let me see if I say twice of f of 10. And so what it's doing, yeah, so here it's working. So it's just gonna take this value 10, and it's gonna apply twice times 10 to twice the times 10 function to it. So 10 times 10, 100 times another 10 is 1,000, and that's how we end up with that. And yeah, so essentially the question is just the type of this function twice, and there's the type of it.
Brink,
yes,
sorry, can I
Yorick.
just jump in again? So
yes,
you can actually take twice of f, right, without the 10.
So sure. So so I can, for example, say g equals twice of f. And now I can say, well, what is g of 5? But something I can't do is if I just say g. So the question, the thing is, yeah, it's essentially complaining, or what it's telling me, and we'll also look at that a little bit today. There's the show type class, which essentially means the type has a toString method. If I sort of talk in Java parlance, so sort of what you see in other languages. So it doesn't have a way to sort of make a string representation of a function. So that's why I can't say, well, just type G and say print it out, since it doesn't have a toString. And that's why I was sort of careful, and every time. So even though I can just say twice of f, I can't really give you a string representation of that. I can just give you a string representation when I apply that function.
This is quite useful for things like automatic differentiation. So you can give a function and you can say, make the derivative of this function, which is a new function, and then you can apply it that way.
Yeah, exactly. So semi-related. So I can't remember if we sort of mentioned that last time, but let's just do something very simple. So let me define a function add that just adds two values. And here I'm sort of doing the same. And the thing is, with these two functions, they are actually not the same. So if we look at the type of add prime, we get this type. And the way you should read this is what add prime is. If you give it one parameter, it will return a function. So if you give it one parameter, numeric parameter a, it will give you a function that takes a to a. So if you give it an x, it will give you a function that takes y to x plus y. And this is completely different from if I look at the type of add double prime. Since add double prime, that's sort of more like what you see in other languages. It's taking a tuple of values and returning a single value. So, and this is what people also refer to as currying, coming from Haskell be curry. That's where the terminology is coming from. So essentially what you can do, or what's the advantage of this whole currying idea? I can make a new function, add one, and this is simply equal to add one. Sorry, let me just. So now I'm making a new function and I'm saying, well, it's this old function and I'm just applying one of the parameters. And now obviously that's just adding one to anything. So add one of 10 will just be 11.
Otto says it's parameterized functions. And yes.
Yeah, let me just see. Yeah. Okay, so maybe something else to move on to is to do a few more examples on list comprehension. So let's try and write a function that do the following. Say I give it some lists of lists. So yeah, I'm just giving maybe 3, 4. So in this case, I'm just giving a list and it's got 2 values in it. So what I want to do with this list, I just want to flatten it. So if I have a list with 2 lists, I just want to flatten it to a single list and just put the values down. So let's see if we can write a function that will do this in general to lists. And let's just call it, say, I'm not sure if there's already one, so I'll just call it concat prime. And typically what you would do sort of, it's not just x's, it's x's with an additional s to sort of give the indication it's nested list of lists. So let's see how we can do this using list comprehension. So one thing we can do is what we can do is we can say, well, out of this list of lists, this x's, let's take a list out of this. And now that I have this list, let me take an x out of it. And I guess I just need an equal sign there. And I guess I just need an x there. Okay, so at least normally in Haskell, if the type works out right, there's a high probability that you might be right. So we can see the type is right. It's going to take a list of lists, and the A is, there's no restriction, and the A is a type parameter. And it's just going to take a list of lists and give me a single list back. And let's see if it's working the way it should. And so if I just go concat, and I just take this list that I have up here. And without that comma there. Oh, so hopefully that I'm lucky. Except with Zoom, everything got frozen there for a while. Oh, it will teach me to make mistakes. Okay, hopefully, let me just check. No syntax. Oh. Yeah, seems I'm not quite awake here. There we go. Okay, so that is just list comprehensions. And here I essentially just did some flattening of a list. So let's maybe with list comprehension, let's take some classic, really elementary math example. And this is sort of also normally one of the first examples they show you with Haskell and list comprehensions. And it's not, I agree, the implementation is not the most efficient, but 100, it should give me all prime numbers up to 100. So let's implement some functions so that if I say primes of 100, it should just go 2, 3, 5, 7, 11, 13, and so on. Just using this whole idea of list comprehension that I've shown you. And as I said, it's maybe not the most efficient way, but it's still fun seeing it the first time. So to do that, let's first implement a function factors that if I give it some number n, it will give me all the factors of n. So if I give it 10, it should tell me, well, I have the factor 1, 2, 5, and 10. And then if I have that for prime numbers, I can just check, is the factors the number 1 and the number itself. So let's see. So again, yes, just driving home this whole idea of list comprehension. So I want to make a new list, and this new list should be the factors of n. So that should just be all numbers x. X should be some number between 1 and n. But we need some additional condition. If we look at n and mod x, that should be equal to 0. And the reason why I use these backticks is the mod function, you are supposed to use it in prefix notation. And if you want to change from prefix to infix, you have to put these backticks in front. So, so normally you would use mod as 10, mod 10 2, that's 0. But putting the backticks, I can write 10 mod 2. So it's just changing from prefix to infix, also vice versa. So something like plus that you would normally use an infix, I can put parentheses around it. And then I can, instead of using it in infix, I can use a prefix version of it. Okay, so let's just see if this is working. So now I can just say factors of 100. And maybe I didn't reload. And yeah, so now we almost at the point we can get all the prime numbers up to n. So let's just implement primes n. And so let's just wonder when something will be prime. So those will be all x's. So what we do is we take the x, so this is prime numbers all the way to n. So we look at everything from 2 to n, and then we should determine whether x is a prime or not. And what we can do to check if it's a prime what we want is we simply want I'm just wondering if I remember the syntax correctly. So we simply want factors of x to be equal to 1 and the number x itself. Okay, let's see if that's working. And there we go. So first, I'm just taking a number between 2 and n. And then the second condition will just filter out and just give me back those x's that I want in the list. So this filtering condition is saying, well, I just want the x's with the factors 1 and x. So again, not super efficient, but sort of fun to see the first time. Okay, any questions about? No new questions. So something else I want to talk a little bit about today is some higher order functions. So sort of the prime example of higher order functions are these functions fold left and fold right. And what they do, yeah, go ahead.
I think there was just a question. So it's the comma playing the role of and in the list comprehension.
Yes, yes. So yeah. So so sort of, yeah, but if you can sort of see it in both these examples. So so you take the x and you want this condition. I should actually check it if I give 2 conditions just to make sure every time it works that way.
But I don't think it's equivalent, right? Because it's sequential. You need to know something about the first condition to say the second condition. And
yeah, so it's not as if so it's definitely, it will complain if I, well, so for example, so well, yeah, let me see. So I don't think I can flip them around. So if I go so I don't think it will be happy with this. So now it will tell me the x is not in scope. So since it before, when I had this, it knew, as you said, it's sequential. It knew what the x is, and then it looked at the second condition. But when I swap them around, then it's saying, well, the x is out of scope since it doesn't really know what the x is referring to. So I have to go with this first. So it's sequential, otherwise it won't know what the x is referring to. And then I need the factors of x is equal to just 1 and x. Yeah, so also, yeah, Yorick, you asked me a question, or you sort of had the suggestion via email, sort of this whole issue, say typically what people will find initially a stumbling block, and this whole idea of, say, things like loops and so on, and the fact that we're using recursion instead of loops, and getting used to that, and so on. So again, I don't have yet a good explanation of all of that to explain nicely, but sort of fold left will sort of be a higher order function that abstracts away recursion. So instead of having explicitly to sort of write the recursive code by pattern matching, I'll just use fold left or fold right, and that will do recursion for me. So so initially, when you see the type signature of fold, it's going to look a little on the scary side.
Sorry, Brink, just a follow-up question about the comma again in the list comprehensions. So it allows multiple lines of code. I think that just means multiple statements for what should be in the returned list. And I think, well, maybe you should answer, but yes. So it's multiple conditions essentially. So
yeah, and as we, yeah, so 100%. And as we saw sort of, and also as you mentioned, sort of the second or the third condition can sort of depend on the first condition. So yeah, it's essentially multiple lines of code. So just one after the other on the same line.
Did that answer the question? Sorry, Sumaya, I don't know if that's quite what you meant.
Yeah, so
yeah, good.
Thank you. So with this, so now the whole idea is I want to show you these higher order functions, fold left and fold right, and they abstract away recursion. So instead of many things that you might implement with recursion, you'll rather just use these fold functions. So sort of today or later in the week, sort of a nice exercise is to try and implement your own version of fold. So you'll see here at the moment, this looks a little scary. And so for foldable, so it's telling me this T must be something which is foldable. So just to make it manageable and understandable for now, I'll just regard this T as being a list. So if you find this scary, just read the foldable T as I'm talking about a list for the moment. And later on, we'll see, well, okay, it could be a tree as well. It's not only, say, a list that's foldable. We can make many things foldable, and we'll see what's required to make something foldable. But for the moment, see it as a list, and we'll be able to fold it up. And also, just my first example, just so that you can sort of just in baby steps get used to it, make the B, just read the B's also as A's. So what you need is you need a parameter that take 2 A's and give you another A. You need a starting A value. You have the list of A's, and then you get an A back. So say for example, so this is already implemented, but say we want to implement with a fold our own version of sum. And what it should do is it should just take this list from 1 to 10 and just sum it all up. So in this case, so the A is the type of the stuff inside the list. So in my case, it's just ints. And so the B for the moment is that's also ints. So we need some function that given 2 ints, give me back a third int. So we want to do that. So let's see, how about if we do sum prime of x's, let's just say, how about fold left? We do plus, and I'll take you through it now, and we'll do 0, and we have our list of x's. And obviously the linter will tell me, well, you're doing something that's already implemented, and that's why the yellow line is under it. So what the plus is doing is, no, let's start with the 0. That's this value B down here. And that's just the value that we start. Before we've looked at anything inside the list, we start with 0. And we call that the accumulator. So then what the plus do, it's this parameter here. And so it's taking the 0 and the next element in the list. So in my case, it's 1, and it gives me 1 back. And then it will take the 1, take the next element in the list, which is a 2, and gives me 3 back. And keep going on like that. So we're folding up the list with plus, and we're starting with 0. Now, another way, if you find this confusing, another way to think of it is the following. So remember, with lists, we talked about it last time. A list is really 1 cons, and then I have the rest of the list. 2 cons, 3 cons. And what this fold is doing is saying simply, well, at least in this basic case, this cons of mine, just replace it with the plus. You should start with 0, but apart from that minor technicality, we just replace all the cons operators by plus. Okay, so let's see if this is working. Reload. So if we do sum prime, 1 to 10, we end up with 55. So instead of having your loop that you would do with recursion, and with recursion you calculate something, you often just fold over some structure. And the structure must be foldable. So in this case, lists will be foldable. And so, yeah, so we just fold it over the list.
Brink,
Yes.
can I ask? So I find this is a relatively easy to understand example because I can easily map how the syntax changes. And could you do something like maximum, finding the maximum element in the list in a similar way?
Yeah, so let's see if we can do that together. So
do you want a suggestion? So max, we would just probably make a less equal instead of plus.
yeah, so then we need some other function here. So just the
maximum of a pair, probably.
So let's just see. So if we have sort of the previous, if we have the previous max and the next element y in the list. So here's the previous max, the next element in the list. Then now I can't remember if there's already a max in the standard prelude. Let's hope so. XY. Yes. So here, yeah, I'm just using the lambda function.
But max takes, it's not tuple, is it?
Well, so let's quickly check here what max want. Yeah, so it doesn't like that. So I should give the parameters one after the other. Right, that's better. And so really, I should give it some min integer value or whatever, obviously, but let's just to make the example trivial, let's just say, okay, there's not negative numbers to sort of, obviously have negative numbers, you can't start the whole calculation with 0, but let's make that simplifying assumption. So let's just call this max.
You could also take the head of the list, am I right?
So there's also, let me just check fold prime, fold left prime. Well, fold left. Oh, come on. Fold left is not as so. Okay, so maybe it's fold left 1. Let me, okay. Let me just see. So I'm not 100%. So let's see if it's going to work. So I think this fold left 1, then I don't have to give it a first element. It's going to start with the head. So let's see if I do this fold left 1 and then see. So if we go max prime to 1, then minus 5. Yep. So yeah, so that's
good.
And so let's do a more complicated example where we let's try its counterpart, fold right, and let's use fold right to do a reverse of a list. So let's implement reverse with fold right. See if we can figure that out. So again, with these things, I always have to look at the types, fold right, to see what it wants. So here's fold right. And okay, so again, we'll sort of, for the moment, foldable T, I'll just replace that and think of T is really a list. So that's what I'll think about, but I'll make it more complicated. And the B's and the A's, I'll now with this reverse example of mine, they'll do different things. And this B is really, people call it accumulator. So it accumulates the partial answers of your whole computation. So A is sort of the next element in your list. B is your accumulated answer thus far, and that B is giving the new accumulated value.
I think it might be very useful to see the type of fold L right below fold R, so you can see just how little it changes in a way.
A good idea. So yes, so it's essentially just the order of those two parameters that's switched around, and that's why I always have to remind myself of the type, since I can never remember whether when I work with fold left or fold right, whether it's in this order or whether it's in this order. Since it's so close together, I always often get 50% of the time get it wrong. So yeah, so let's see if we can do reverse. So let's do our own reverse of some list, and we want to do a fold right, and we'll have some function here. And so initially, so now this B is sort of what we start with. So I suppose I can also implement it with sort of the equivalent fold right one or something like that. I don't really need a starting value, but let's just keep it simple, have a starting value. So initially I'll start with the empty list, and then I'll update this empty list as I reverse my list. And it's the list of X's that I want to reverse. So it's essentially this function that takes the accumulator, the next list element, gives me a new accumulator. And so folding right, you should think of, you step through your list from the back to the front. So let's see. So what we have is we have the accumulator, and we have the next list element. Let's see if this is going to work. So if we do,
Would you be consing them?
yeah, I have to, but I'm now trying to think, and well, I guess I should.
I feel like it should be just y:x, but maybe I'm misreading it.
Yeah, you 100%. What confused me for a while, I was looking at this type signature instead of this one, and now that yeah, exactly. Once I look at the right type signature, that's exactly what we want. So essentially, this B, what we want is it should be the Y, which is a list. So now, in this case, the B is a list, and the A is just some generic type like an int. So think perhaps of the A as the int and the B as your list. And the final answer that you should get should also be of the list type. So if I look here, that is the next element in my list. But I'm now also wondering, okay, so perhaps I'm gonna change my mind there, and let's also do this. Should we do this with a fold left? Let's see which one works the best. So we start with the empty. Well, let's see if it's working, and then we try and explain it if it's working. Otherwise, we do. So if we do reload, and we reverse the list from 1 to 10. It's reversing. So let's see why it's working. If we look at the types, okay. So you start right from the back of the list with the empty list. So now what you do is you take the last element and the empty list, and you apply this operation. And it's just going to give you the list with the last element. Right, so every time you sort of repeat this, the fact that you sort of switching the order. So the A is sort of the previous element in the list as you step through from the right to the left. But every time sort of the list that you've accumulated thus far and the next element, you do this concat in the opposite order. So that's a list, and that's a list just with the single next element. And sort of, if you think recursively about it, that's why that lambda function there will reverse the list for you.
It looks like it's just a matter of convenience, right? Fold R and fold L have just the first two arguments switched. So you should be able to always translate one to the other, probably, right?
I'm pretty sure, yeah, you should be. And I guess now that also, yeah, I'm pretty sure, since another reason why I'm saying that is the following. If I look at this foldable type class, we notice it's got various things like fold right, fold map, fold left. But at a minimum, you need fold map or you need fold right. So in other words, what this is telling me, I can make something foldable by implementing a fold right for it. And then since it's foldable, I'll be able to call fold left on it. So I can make any data type foldable by specifying a fold right for it. And if I have a fold right, I can call all these things. Yeah, so maybe that's a bit too high level at this moment, but yeah, it's sort of handy using this info statement, just seeing what something foldable is, and sort of, yeah, what I'm sort of trying to convince you about is the fact to make something foldable, I need either a fold map or a fold right. And if I have a fold right, I can call all these other folds. So there's a default implementation that say, well, if you have fold right, this is how you do fold left. Yeah, so I'll maybe next time show you example where I say I make a tree foldable by implementing a fold map or something like that. So maybe it will be handy to sort of show you how I make something foldable by making, say, a tree foldable. So that might be a good idea. Okay, so any other questions? So let's see, last minute or so. So let me give you one quite easy example exercise. So here in chapter 5, see if you can do this exercise 1, where you just use list comprehension. And what it should do is you want to calculate Pythagorean triples. So if you give pyths of 5, it should return 3, 4, 5 and 4, 3, 5. And just see how the change that you should add so that it gives you only this first tuple and not the second one as well. So maybe as a nice easy exercise, do this from chapter 5, this first exercise. And if you want something more difficult, see if so. Last thing I'll say, so see if you can implement your own fold left prime. And so look at the signature fold left, but maybe just do it for lists, just to keep it simple. And if you want to, you can decide whether you want the types A's and B. So if I look at the type signature of fold left, decide initially maybe have the A's and the B's the same type, but later sort of do it sort of more in this proper way, but maybe don't do it for something foldable, just do it for lists. So see if you can implement, if you want a harder exercise, if you can write the code for your own fold left, but just on lists. And essentially you'll just do it by recursion. So you're abstracting recursion with using recursion or something along those lines. Okay, so I hope we'll see all of you again in a week's time.
Yeah, thank you very much, Brink, for for continuing our Haskell education. Yeah, no, that's really very nice. I think that slowly we are starting to understand the philosophy behind how Haskell operates. We had already a few questions in between. I don't know if participants have further questions, and if they want to ask the question in person, they are welcome to raise their hand and we can give them the right to speak immediately.
I can so long answer. Zerop ask, yes, it's a fold or these folds, they just functions like any other function. And people sort of refer to them as higher order functions since they take functions as parameters. As you saw, sort of we specified this lambda function. So for example, with the reversing, we had an element in a list and then we sort of concatenated those. So you had a lambda function, and that's why you call it a higher order function, since it takes a function as a parameter. And yeah, but it's just a function like any other function. And the idea is that it abstracts recursion, and the Haskell compiler got all kinds of optimizations that kicks in if you do things with fold left. So you'll get better performance with fold left and fold right compared to when you write your own recursive code.
Yeah, there doesn't seem to be any other question at the moment. I think probably it's important that everyone plays a little bit with Haskell to see if they can reproduce what you did, and if we can solve the exercise that you suggested. I think that the only last thing that I would like to add is again to extend the invitation to the participants and to the speakers. If they want to chat 5 minutes in a less formal environment, we could move to Kumo space as we usually do, and have a quick chat there, and maybe in a less formal environment, other questions come up that I'm sure Brink and Yorick will be happy to answer. Otherwise, thank you very much, everyone. Sorry for the slightly chaotic start, but it coincided with a power failure on my side.
So sorry, Francisco, just remind me again the URL for your Kumo space.
I just put it in the chat.
You just that.
It just at one of the last messages in the chat.
Sorry. Oh, cool. Thanks a lot.
You just click on the link and you should be in business. Yeah. Okay, perfect. Then I hope to see most of you in Kumo space just now. The drinks are free. Yeah. So I see you there. Thank you very much. Have a good rest of the day. Yeah. and enjoy the electricity if you have. Yeah. Thank you.